Next work energy question is from year 2007, and if you have a look at that, the trolley is moving with constant velocity, so that's an important point. At constant with a constant velocity, so the resultant force acting on the trolley is going to be zero. Resultant force acting on the trolley is going to be zero, right? Three men ABC are pulling the three strings in such a way that their tensions are T1, T2, and T3 respectively. As shown in the figure, when the trolley moves a distance L, the work done by the men are. Right. Now, normally when there is an object like this, on a smooth plane, if you apply a force of F on that object, and if the object is moving like this, under the influence of the same force for distance of L, then we all know work done has to be what? Force into distance, force into displacement in the direction of the force, F into L. Now, here the ground was stationary. So when you give a force, the object will be moving. But in this question, the problem is these men are standing on a moving trolley. They are not standing on the ground, which is stationary ground like this. That's not the case. All right. And you can see, first and foremost, the object is moving to the right. It is indicated by the direction of its velocity. And definitely the work done by this person is zero. Why is that? Work done by this person is zero. The reason I can say that is force is perpendicular to direction of motion. When the force is perpendicular to direction of motion, that in force work equal to force into displacement in the direction of force. Now, if force was like this, no problem. The same force above had been like this, no problem, because you can still take the component of that force. Now, if this is F, then you can take a component. But if the force is vertical when the object is moving horizontal, then it is perpendicular. Therefore, the work done by C is definitely zero. So it's one of these four answers. This is definitely wrong. Now, when you take the other two people, if you consider the forces acting on them carefully, acting on the person carefully, now the person is pulling the string to the right. String will pull the person to the left, applying a T2 force. And what else? There will be a perpendicular reaction acting on the man's leg, and there will be a friction acting on man's leg as well, like this friction. Because now you can see the man, if the man is slanted like this, he is pushing the ground or the bottom part of the trolley to the right. So trolley will push him backwards, and there will be weight acting on the man as well. Right. So the issue is now the man is applying a force of T2, true, but that if you consider equilibrium of man, now man is at rest with respect to what? With respect to trolley. Man is not moving now with respect to trolley. So if you take the resultant forces acting on the man, you can say the horizontal force acting on the man should be equal to the other force. Right? So what is horizontal force acting on the man? The frictional force. Equal to what is the force acting towards, I'll just put FF for friction. What is the force acting towards left side on the man? That is T2. Okay, these are the forces acting on the man. Now, what are the forces acting on the trolley? Because of that, on the trolley, there will be a tension acting like this, no? T2. And also, this F in blue color is the force given by the trolley bed to the man's legs. So the for a man's leg will exert a force on the trolley as well, like this. And that is our FF. Okay, that is FF. Hope you can understand this. Man is pushing the trolley. So that force is this, and man is pulling the trolley with the string. That force is this. And again, we know T2 and FF are equal in magnitude. Okay. So if you think when the man pulls the trolley, he is exerting only a force of T2, that is completely wrong. Okay, with his hands, he is exerting a force T2. With his legs, he is exerting the force FF. Therefore, both the forces, since they are equal, resultant force exerted by A, resultant force exerted by A on trolley, it's how much? That is 0. Okay. If only T2 was there, then okay. For that, he'll have to be floating then. He will have to do it while floating. And that's not possible. He should be in contact with the bottom of the surface. So he is actually, from with his body, he is applying two forces. One is the tension, one is the force given by the leg to the trolley bed. Both are equal. Therefore, resultant force is exerted by A is 0. So what is the work done by A? Work done by A will also be 0. Similarly, we can do the same analogy. No, I was talking about B all this time. Sorry, I was talking about B all this time. Sorry, I was talking about B all this time. Yeah, I was talking about B all this time. Extremely sorry about that. B. Resultant force exerted by B on trolley is 0. So work done by B. Work done by B is 0. Similarly, look at C. So look at A. Sorry, look at A. Look at A. You can do the same analogy, right? Similarly, work done by A is also 0, because I don't have to draw everything again and explain it to you. It's quite identical, right? Look at A and look at B. They are on either side. Right. A is exerting a force of, now I'll mark the forces acting on the trolley in green color. T1 will be acting on trolley like this, and by man's leg, a frictional force will be acting like this. And similarly on A, what are the forces acting on A? The string will be pulling him to the right, and flow will be giving a force like this, Ff. And we know Ff is equal to T1. Therefore, resultant force is 0. So work done by A is also 0. So our answer should be fifth one. You might get carried away just considering the tension, because when you consider just the tension T2, then you might think T2L is the answer. But unfortunately, it's not only the tension, which is the force exerted by the man on the trolley. It's also the friction acting at the bottom. Now, if there is no friction acting at the bottom, he can't stay this way, people. He will fall. He will fall, slip and fall down. Without friction, a man can't stand this. Okay, so you should not have any doubt about that. Fine. So that's it. The answer for this question is fifth one. Next question is from 2008. When a ball of mass 0.1 kilogram is thrown vertically upwards in a vacuum, so you know vacuum means no air resistance. No air is there. That's what vacuum means. It reaches a maximum height of 5 meters. So let's draw that in vacuum. You are throwing the ball at an initial velocity. Have they told that? They have not given the initial velocity. I'll say take it as u. Okay, and the object goes up and reaches the maximum height. Final velocity is 0, and the maximum height reached by the object is given by 5 meters. Yeah, okay, that is 5 meters, right, in vacuum. Yeah, and the mass of the object is given. Keep that in mind. That is required 0.1 kilogram. Now let's finish it off here, people. This is A. Okay, this is the starting point, and this is the finishing point B. Let's consider energy here. Energy. What is the energy available here? So initially, I'll take this as my zero potential level. If I take this as my zero potential level, what is the meaning of that one? Gravitational potential energy at this level is 0. From this level only, I have to measure the height. So at A, we have only kinetic energy. So kinetic energy at A should be equal to gravitational potential energy at B. What is the kinetic energy at A? Half mv squared. Gravitational potential energy at B, mgh. M and M can be cancelled out. So V squared equals to GH. So U squared in this case, that's equal to 2 into 10 into 5. I'll take it as 100 then. I'll keep it that way, right? 100. That is U squared. And then what are they doing? When the ball is thrown upward with the same velocity in air, it reaches a maximum height of 2 meters. So in air, when you throw the ball vertically upwards, what's happening? It's not reaching the same height as before. It is just reaching a height of 2 meters. And its velocity becomes 0. But I think it should be thrown at the same velocity. If not, you can't do the comparison, right? If not, they should mention any relationship between the velocities. But anyways, they have told it's thrown at the same initial velocity, 0.1 kilogram, and the height reached by the object is just 2 meters. Right. Why does that happen? Initially, all the kinetic energy here at the bottom was converted to potential energy. But now, this is 2 meters. Okay, again, this I'll take this as my zero potential level. Initially, we have kinetic energy. Gravitational potential energy is 0, true. But that kinetic energy, now a part of that, just a part of that will be converted to potential energy. Another part of that is being used to perform work against air resistance. Now the question is the average resistive force exerted on ball by air. So in this question, you have to consider air resistance. The problem in this question, people, air resistance is not constant. It will change as the velocity changes. But for this question, we have to take it as constant and only do it because they are asking for the average resistive force. All right, fine. So let's see if you can understand. Let's start. I'll take this point as A again because same point. And now a new point, the object reaches a new height. That is, let's take that point as C. So I'll start. Initially, you have kinetic energy at A. All right. And that kinetic energy is converted to gravitational potential energy at C. Plus, a part of that kinetic energy is consumed to perform work against friction, work against air resistance, work against air resistance. Now, that is the issue here. All that kinetic energy is not converted to potential energy. A part of that is wasted. Now, what is the kinetic energy at A? It's again half mu squared equal to gravitational potential energy at C is mgh plus work against air resistance. That is, I'll take the average resistive force as F, which we are supposed to find out. That is FH. Why am I putting FH? Height is h. F into h, force into distance traveled. So height, if it is the object is traveling a height of 2 meters, it has traveled 2 meter distance to find the work done. Okay. Now from this equation, you can't get rid of mass. That's why mass is important in this question. So let's finish it off. Half into, for mass 0.1 into, for u squared, we have already calculated the value, that is 100, equal to for m 0.1 into g 10 into height. Height is 2 meters. Height is 2 meters. All right. Plus, then average resistive force we have to find out into the distance traveled is 2. Okay, then you'll be getting 5 here. You'll be getting 2 here plus 2f. So I'm getting 2f equal to 3 and f is equal to 1.5 Newton. That is the average resistive force. Now, according to this question, I have considered like the resistive force is constant. That's why I directly put F into H. But in reality, it doesn't happen that way. In reality, it doesn't happen that way. As the object goes up, its velocity reduces. Resistive force will also reduce with that. So the questions will get a little complicated if you consider the exact situation. That's why they are asking for average resistive force. So we can assume that the resistive force was constant throughout, and that value is the average resistive. With that assumption, we can get this answer, 1.5 Newton, and that would be the first answer. Next one is from 2010, the next question. The graph shows the variation of force F exerted on an object P when it is moving along x-axis from x equal to -5 to x equal to 5. The work done on the object by the force is, right. Now this is a force distance graph, and they are applying the force from -2 to 3. That is how the force is applied. So you have to understand one thing carefully. You have to interpret this diagram carefully. What is the interpretation here? Now, this is what's actually happening. There is a horizontal path or whatever it is, horizontal path, a horizontal surface, and on that, there is this point. This is like the point where they have taken the displacement to be 0, right? So the box is initially the box. So I'll just consider it as a box. Okay, an object, right? Fine. The box is initially here, 2 meters to the left of the starting point, and it's moved like this. This is the meaning of that, diagram. They are applying a force of 10 Newton, such that the box from the starting point, initially it is at 2 meters to the left, and then finally it is at 3 meters to the right. This is the explanation for this diagram. All right. So if you see in reality, if you see from outside, we have applied a 10 Newton force, and the object has moved overall. What distance? How far has the object moved overall? How far has the object moved overall? It has moved a distance of 5 meters, hasn't it? We have applied the force of 10 Newton. It has moved a distance of 5 meters. So work done, it's very simple. Work done, we know that is equal to force into displacement in the direction of force. So 10 into 5, that is 50 joules. Okay. Yeah, it's true that this part of the graph is on the negative side. We don't subtract that. We don't do that because this is the interpretation for this diagram. So overall, the object has moved 5 meters under the influence of 10 Newton constant force. That's it. All right. Fine. So the answer for that question is fourth one. Right, guys, I hope that is okay, no? Shetana. Next question is from 2011, and this question speaks about collisions. A particle of mass m1 moving with speed v along plus x direction collides elastically with another particle which is at rest. Okay, the next particle is m2. So mass m1, it's moving at speed v towards mass m2, which is initially at rest. This is just before the collision. Just before collision. Right, and the collision is, people, elastic. The collision is elastic, right? So if collision is elastic, let's analyze what will happen. If collision is elastic, if the collision is elastic, first case, when m1 and m2 are equal, if m1 and m2 are equal, then you can expect this after the collision. m1 will come to rest, m2 will move with the same initial velocity of m1. This will happen if they both have the same mass. Okay, because the kinetic energy has to be conserved. So half mv squared, 0 kinetic energy. After the collision, half mv squared, 0 kinetic energy. mv, momentum, everything is conserved. Second one, if m1 is smaller than m2, what happens is m1 will recoil at a new speed. We'll take it as v1, and m2 will move to the other side like this. All right, fine, because m2 is heavier, so m1 will bounce back, but m2 will also move. There is a force exerted by m1 on this, so it will move. And the last case, if m1 in case is larger than m2, then you can expect this to happen. Both m1 and m2 will move in the same direction. m1 and m2 will move in the same direction, but m2 will move faster than m1. m2 will move faster than m1. It won't stop. This will happen. Okay. But one thing which will never happen is this. Both m1, m2 combine to form a single object. That is never going to happen. Okay. That is something I want to stress. m1 and m2 will not combine if the collision is elastic. Because when two objects combine, what will happen? There will be loss of energy. When they collide, there will be heat energy released, there will be sound created, there will be light created sometimes, because energy will be lost. So that cannot happen. Combining, if two objects have combined, that's no longer an elastic collision. Okay, elastic means energy loss is 0, no energy loss. That is what elastic collision means. Right. So definitely the answer for this should be C. Very direct, because M1 and M2 would move together. That is incorrect. They can't combine like that, because when during combination, when two objects combine, they can't just combine. Okay. A lot of energy will be wasted. That's why C should be incorrect. They are looking for the incorrect statement about elastic collision. Right. So this is important. Collide elastical. Right. So we can settle to answer C.